All right, so we're diving into this universal transformer paper, and you've given me quite the stack of research here.
Yeah.
I get other papers, study guides, timelines. It seems like you want the full picture of how these universal transformers work,
Yes.
but also how they fit into like the evolution of machine learning.
That's right.
We're going for the deep dive here.
Indeed. It's not enough to just know the mechanics, right? We need to understand the challenges that these UTs are trying to address
Right.
and how they stack up against existing models.
Exactly. And there's this intriguing idea that UTs could be a step towards more general purpose AI.
Yeah.
But before we get ahead of ourselves, let's start with the basics.
Okay.
The UT paper, it frames itself as a solution to some inherent limitations in traditional recurrent neural networks.
Uh-huh.
What's the issue with RNNs in the first place?
Well, RNNs are great at processing sequential data, like text or time series, because they take into account the order of the elements.
Yeah.
But this strength becomes a bottleneck.
Okay.
They process information step by step,
Okay.
making them slow to train, especially with long sequences.
So it's like reading a book one word at a time.
Yes,
You get the sequence, but it takes a while to grasp like the whole story.
precisely. And that's where the transformer model comes in.
Okay.
By utilizing self-attention mechanisms, it can process the entire sequence in parallel, leading to significantly faster training times.
So it's like reading the entire book at once,
Yeah,
grasping all the connections and nuances simultaneously.
yeah.
Sounds almost superhuman.
It's a powerful approach, no doubt. But it turns out that the transformer, while revolutionary, isn't a perfect solution either.
Okay.
There are certain tasks where RNNs still outperform transformers,
Interesting.
especially those that require iterative or recursive processing.
So each architecture has its strengths and weaknesses.
Yeah,
Which brings us to the universal transformer.
right,
Aims to combine the best of both worlds.
right.
How does it manage this?
The key innovation lies in what the researchers called parallel in time recurrence.
Okay.
So imagine multiple RNNs,
Okay.
each working on a single element of the sequence simultaneously.
Okay.
These RNNs then communicate with each other through a self-attention mechanism, refining their understanding of the sequence with each step.
So instead of a single RNN trudging through the sequence, we have a whole team of them working in parallel.
Yes,
But how do they refine their understanding? I'm guessing self-attention plays a crucial role here.
it's not just guessing, it's the core of the mechanism.
Okay.
Self-attention allows each RNN to gather information from all other RNNs, creating a richer context for understanding its own element.
So each RNN gets a glimpse of the bigger picture,
Yes.
not just its own little piece.
Right.
This parallel processing with recurrent steps seems like the key to the UT's power.
Uh-huh.
But there's another element the paper highlights, dynamic halting.
Yeah.
What is that all about?
Dynamic halting allows the UT to allocate resources intelligently.
Okay.
Instead of performing a fixed number of recurrent steps for every element, it can dynamically decide how many steps are needed for each one.
So some elements might require more thinking than others.
Exactly.
How does the UT decide how much attention to give each element?
It utilizes a mechanism inspired by adaptive computation time.
Okay.
The UT essentially assesses the complexity of each element and adjusts the number of processing steps accordingly.
Huh.
This not only improves efficiency, but can also lead to better accuracy.
It's like the UT is saying, this element seems straightforward. I don't need to dwell on it, but that one over there is tricky. Let's give it some extra attention.
Yeah.
Now, the paper makes a bold claim about the UT being computationally universal. What are the implications of that?
It means that theoretically the UT has the same computational power as a Turing machine.
Okay.
Given enough memory, it can perform any computation that a Turing machine can.
And a Turing machine is essentially a theoretical model of a computer capable of executing any algorithm.
That's right.
So are they saying the UT is in theory as powerful as any computer? That seems like a significant leap.
It is. The standard transformer with its fixed number of layers is inherently limited in its computational depth.
Right.
The UT, however, can theoretically overcome this limitation.
So the UT could potentially tackle problems that the standard transformer simply couldn't handle no matter how much you tweak its parameters?
Exactly.
But how does this theoretical power translate into actual performance?
Right.
The paper highlights the UT's effectiveness in various experiments, starting with the BABI question answering dataset.
Yes.
What makes this dataset so challenging?
BABI tasks present short stories that require different types of reasoning to answer questions correctly.
Okay.
The standard transformer actually struggles with these tasks,
Interesting.
highlighting its limitations in scenarios demanding a more iterative, reasoning-based approach.
But the UT excelled in this domain.
It did, and it didn't stop there.
Okay.
The UT achieves state-of-the-art results on the LAMBADA language modeling task,
Right.
surpassing both LSTMs and the standard transformer,
Wow.
especially when incorporating dynamic halting.
So the UT is not just a fast learner, but also a clever one.
Uh-huh.
The dynamic halting seems to be a key factor in its superior performance. But I understand the UT's capabilities extend beyond language-based tasks.
Absolutely. The paper also explores its performance on algorithmic tasks,
Interesting.
copying, reversing, and even adding sequences of numbers.
Okay.
Tasks typically considered more in the realm of traditional computer programs.
If it's not just a language whiz,
Uh-huh.
it's an algorithm cruncher too. And in these algorithm tasks, how did it compare to the competition?
It consistently outperformed both LSTNs and the standard transformer, demonstrating its remarkable versatility. This model is living up to its universal name.
It certainly seems that way. But before they delve further into the UT's performance and its potential implications,
Okay.
there's one more question I have.
Okay.
How does the UT relate to other, even more powerful models like neural GPUs or neural Turing machines?
Right.
Are they doing something similar under the hood?
There are some similarities, particularly in their capacity for iterative refinement of representations,
Okay.
but neural GPUs and neural Turing machines, while powerful in theory, often struggle with real-world messy data like natural language.
So they're more like theoretical giants that haven't quite figured out how to navigate the real world.
You could say that the UT, on the other hand, seems to bridge that gap.
Okay.
It's computationally powerful enough to handle complex algorithmic tasks, but also flexible and adaptable enough to excel in the realm of natural language.
It's a fascinating proposition. This universal model, capable of handling both the theoretical and the practical, the structured and the messy, it's almost as if,
As if we've stumbled upon a new species, a new kind of intelligence that defies our traditional categories.
and that begs the question, what are the implications of such a discovery? What does this tell us about the trajectory of AI research?
I believe the universal transformer represents a paradigm shift, a blurring of the lines between different approaches to machine learning. It challenges this long-held notion that we need specialized models for different tasks. Perhaps we're moving towards a future where a single architecture can handle a wide range of challenges.
It's almost like we've been trying to build separate tools for every job and realizing that maybe, just maybe, we can create one tool that's adaptable enough to handle it all.
A cognitive Swiss Army knife, if you will, but this versatility doesn't come without its complexities.
Right?
The study guide you provided delves into the concept of the UT's recurrent inductive bias.
Okay.
Can you unpack that for me?
Well, it's all about the assumptions the model makes about the data, right?
Yes.
The UT, with its recurrent structure, seems to be biased towards learning tasks that involve sequential logic. It's like expecting the data to have a temporal structure
Yeah,
where each element builds upon what came before.
precisely. This bias is incredibly valuable for many tasks, from understanding the flow of information in a sentence to processing the steps in a mathematical algorithm.
So the UT is not just processing information, it's actively looking for patterns and relationships over time.
That's right.
Is this something the standard transformer lacks?
The standard transformer, with its emphasis on parallel processing, treats each element as largely independent.
Okay.
While effective for tasks where order isn't crucial, it misses out on this crucial element of temporal understanding.
It's like the difference between seeing a collection of photographs and watching a film. The UT, by incorporating this recurrent bias, is able to understand the unfolding narrative,
Right.
the cause and effect, the way one event leads to another.
And it's this combination, parallel processing and recurrent inductive bias, that gives the UT its edge. It can handle both the simultaneous and the sequential aspects of information. But there's another aspect of the UT's architecture that contributes to this capability:
Okay.
the position and time embeddings.
Right.
Can you explain how those work?
From what I understand, these embeddings are crucial for providing the model with information about the location and order of elements, even when processing the sequence in parallel.
Yes, they provide a framework for understanding both space and time within the sequence.
Okay.
For each element, the UT creates vector representations or embeddings
Right.
that capture its position in the sequence and the current time step in the recurrent process.
So even though the UT is processing everything simultaneously,
Yeah,
it still knows where each piece fits into the bigger picture, both spatially and temporally. It's like giving each element a unique coordinate on a map,
yes.
but the map is constantly evolving with each recurrent step.
A dynamic map of meaning, one could say. These embeddings are crucial for the UT's ability to learn long-range dependencies and complex patterns. They provide the context that allows the model to connect the dots to understand how elements relate to each other across the entire sequence.
The paper mentions that these embeddings are fixed and constant. Does that mean they don't change during training?
That's correct. They are pre-calculated using mathematical functions that create unique patterns for each position and time step. This approach ensures that the model always has access to this spatial and temporal information.
So it's like giving the model a built-in compass and clock,
Right.
helping it navigate the complexities of the sequence.
Exactly.
But that choice also raises an interesting question.
Okay.
If the embeddings are fixed, doesn't that limit the model's flexibility?
It's a trade-off. Fixed embeddings streamline the learning process and ensure consistency,
Right.
but they could potentially constrain the model's ability to adapt to highly irregular or unexpected sequences. This is an area where further research could lead to interesting developments.
Okay.
Perhaps a hybrid approach combining fixed and learnable embeddings could offer the best of both worlds.
That's a fascinating thought. It's like giving the model the ability to adjust its compass and clock based on the specific terrain it's navigating.
Yes.
Speaking of adapting and adjusting, let's talk about the transition function used in the UT. The paper mentions using either a depth-wise separable convolution or a position-wise fully connected layer. Why these particular functions?
These are both types of neural network layers,
Okay.
each with its own advantages and disadvantages.
Okay.
The depth-wise separable convolution is known for its computational efficiency,
Okay.
particularly when dealing with high-dimensional data.
So it's a leaner, more efficient way to process information,
Yes,
especially when dealing with large and complex data sets.
precisely. It's particularly well suited for tasks like image processing, where the data has inherent spatial structure, but the UT also utilizes the position-wise fully connected layer,
Okay.
which is known for its ability to capture intricate relationships between elements.
So it's a more comprehensive approach,
Yeah,
connecting every neuron in one layer to every neuron in the next.
that's right.
But wouldn't that make it Oh, our listeners got something to share. Let's hear it.
Hey, hey there. Thank you for incubation review. So what's the
Oh, hey there. Thanks for tuning in. And I'm not sure exactly what you mean by
Oh yeah, let's hear it.
yeah, I say the weight sharing and what's the connection between the weight sharing and
Okay, hey, chiming in. And it sounds like you're interested in weight sharing.
Yeah, we're happy to hear from you. It seems you want to know about how weight sharing connects to T, right?
Absolutely. We were talking about those different neural network layers the UT uses.
And it sounds like you're picking up on a really important part of how the UT works, so let's unpack it.
We were about to dive into the impact of those layers on efficiency and expressiveness.
Right, how they contribute to the model's adaptability. We can circle back to the other stuff later.
So yeah, you're curious about weight sharing and its connection to the UT.
Exactly. And it's a real Oh, yeah, uh-huh.
yeah, the weight sharing between the cross attention,
Oh yeah. Uh-huh.
weight sharing and the cross attention. So what's the difference between these two?
Okay, that's a fantastic question. You're getting right to the heart of a very interesting distinction.
Yeah, it sounds like you want to know more about how weight sharing features from attention.
We were just about to go into how weight sharing makes the UT efficient.
But it makes sense to clarify this now because they both contribute to how the UT processes information.
So, in short, weight sharing is about reusing the same parameters across the network.
Yeah, like it's about using the same learning filters in different parts of the model.
Exactly. It's about efficiency, reducing the total number of parameters.
And as we were just saying, this sharing happens across all layers and time steps.
But cross-attention is a completely different thing. It's about how the model focuses its attention on different parts of the input.
That's right. Cross-attention lets the model weigh the relevance of different parts of the sequence.
So with self-attention, each part of the input sequence is related to all other parts.
Whereas in cross-attention, you have different sequences connecting with one another.
So weight sharing is about parameter efficiency, and cross-attention is about which parts of the input are most relevant.
They're both important concepts in understanding how the UT works.
Exactly. And with that clarification out of the way, let's get back to weight sharing.
Okay, so as we were saying, weight sharing is about using the same parameters in different parts of the network.
Yes, and in the UT, this means the self-attention and transition function weights are shared across all layers and time steps.
So instead of having a whole set of unique weights for each layer and time step.
Right, it reuses the same ones. This is really similar to how CNNs and RNNs operate.
This reuse of weights is essential for keeping the model efficient especially given the iterative and parallel nature of the UT.
Absolutely. Without weight sharing, the UT would be far more computationally expensive.
And also more prone to overfitting?
Yeah, with fewer parameters, it reduces the chances of overfitting to the training data.
But there's another important aspect to this architecture that allows it to handle complex tasks.
Right, the recurrent step combined with the self-attention mechanism.
That's where the model refines its understanding of the sequence through repeated passes.
Yes. After the self-attention step, the UT uses a transition function to further refine the representations of each symbol.
And this transition function, as we were saying earlier, can be a depth-wise separable convolution or a fully connected layer.
And the choice depends on the specific task at hand and its computational requirements.
But it's this constant back and forth refining of the representations that gives the UT its edge.
Yeah, it allows the model to learn complex relationships and dependencies within the sequence.
But it's not just about refining individual elements.
Right, the self-attention mechanism allows each element to also take into account the context of the entire sequence.
It's a constant feedback loop where each element is simultaneously refining itself and learning from its neighbors.
Exactly, and this is what allows the UT to learn those complex iterative patterns that we talked about. Oh, yeah,
Then what about the transition? The la- the
Okay, hey there. Thanks for chiming in. And it sounds like you're interested in the translation aspect of UT.
Yeah, it's great to hear from you. We appreciate your questions.
We were just talking about the self-attention mechanism and how the UT uses that.
But it's good that you're bringing up translation because that's another domain where the UT. Let's dive into it.
So yeah, it seems that you're curious about how the UT relates to machine translation.
Exactly, and it's a great question because it highlights how versatile the model is.
We actually have some information about that from the research paper.
Right, the paper specifically mentions the UT shows impressive. Oh, go for it.
Actually, I mean the transition functions.
Okay, clarifying. It sounds like you're interested in the specifics of those transition functions.
Yeah, we appreciate you keeping us on track, and it's great to hear you're interested in those details.
We were just about to dive into the machine translation capabilities, so we can come back to that later.
We just mentioned the specific types of transition functions used by the UT, like depth-wise, separable convolutions.
And position-wise, fully connected layers, and we said that the choice depends on the task.
So let's unpack the transition functions.
Okay, as we've already said, the transition function is what the UT uses to further refine the representation of each symbol.
And this transition function is applied after the self-attention step, so it's refining the context of each word.
And the paper says it can be either a depth-wise separable convolution or a position-wise fully connected layer.
So a depth-wise separable convolution is known for its computational efficiency, particularly with high-dimensional data.
It's like a leaner approach to processing information, and it's good for things like image processing.
And the other option for the transition function is the position-wise fully connected layer,
That's known for its ability to capture intricate relationships between elements.
because it connects every neuron in one layer to every neuron in the next.
Yes, but the UT applies this fully connected layer independently to each element in the sequence.
So it's able to really give each element a unique and personalized analysis in the context of the whole sequence.
So both are neural network layers, but they have different strengths and weaknesses.
The convolution is great for efficiency, and the fully connected layer is great for nuance.
And the UT chooses which one to use depending on the specific requirements of the task.
Now, with that clarification about transition functions, let's pivot back to translation.
Right, as we were about to say, the UT shows impressive results in machine translation.
It actually improves upon the standard transformer on the WMT14 dataset.
Yeah, with a 0.9 BLEU improvement, which is pretty substantial.
And we know that the standard transformer is already pretty good at machine translation, right?
It is, but the AT recurrent and self-attentive approach.
Oh, back to our listener. What's up?
Thank you. Can we wrap up the conclusion and main takeaways?
Okay, we hear you, and thanks for letting us know that you'd like us to wrap up.
Absolutely. We appreciate the feedback, and we'll get to the conclusion and takeaways soon.
We were to discuss the translation abilities of the UT, but we can move to a summary.
Yeah, we were just talking about how well UT does in machine translation tasks.
We can briefly mention the dynamic halting and then move into the conclusion and takeaways.
So we were saying that the UT achieves a 0.9 BLEU improvement over the standard transformer on the WMT14 En-De dataset.
Yeah, and it seems to be due to that recurrent and self-attentive approach, which helps it grasp the nuances of language.
And we were about to mention that while dynamic halting helps in other tasks, it doesn't seem to provide a big boost in translation.
It seems the iterative approach is key for translation tasks, and the UT does a great job without dynamic halting.
Okay, so with that, let's move to our conclusion and key takeaways.
Okay, so we've covered a lot in this deep dive, from the limits of RNNs to the rise of the transformer and now the UT.
We've talked about parallel and time recurrence, dynamic halting, and that interesting concept of computational universality.
We explored how the UT excels in different tasks like question answering, language modeling, and machine translation.
And we unpack the concepts of weight sharing, self-attention, embeddings, and transition functions.
We discussed its relation to other models and its recurrent inductive bias, which seems to be one of its strengths.
It really seems like this universal transformer could be a new direction for AI research.
It does, and we're excited to see what happens next and how this model is further improved.
So that's the universal transformer, and it's definitely a model to keep an eye on.
Yeah, we hope that this conversation was informative and gave you a deeper picture of the model.
Thank you for joining us on this deep dive. We really appreciate your engagement and your great questions.
It's always a pleasure discussing these topics with you and exploring these ideas together.
We hope you'll tune in again next time for another deep dive into the world of AI.
Thank you again for listening. It was a great discussion.